of the things that, that I first kind of, when I was getting introduced to Bloomberg, or when actually a recruiter pinged me a couple years back about Bloomberg, I thought, why would a security technologist really want to go work at a financial company? That doesn't really seem like terribly interesting. But what I quickly learned was that actually Bloomberg is a lot more than, actually in fact we're not a financial company, we're actually a data analytics company. I'll talk a little bit more about that, but the project I want to talk to you about today is actually one where we started about a little over a year ago in building private cloud infrastructure. And I've gone to a lot of security conferences and I've seen scads of talks about private clouds, or actually really public clouds, and the security implications of actually running with your company's data in somebody else's infrastructure and all that stuff. That's not what I'm going to be talking about today. Instead, I actually want to focus on the security assurance opportunities that a private cloud infrastructure can actually afford you. And I'm going to talk through a little bit about how we designed our cloud infrastructure. And I'm going to actually point you at a couple of resources, because we actually open sourced all of our recipes for standing these things up, so you can actually do them yourselves if you wanted to. But before I get too far into that, sorry, move this down a little bit, I feel like I'm being really loud. Let me first start off with the fact that, when we first were getting started, we knew that we didn't really know everything about private clouds. We had a lot of smart people that were thinking a lot about it, so we decided to really get some expert advice first. And as Mike mentioned, I used to be at HP Fortify, so I think that's where we turned first.
Hewlett-Packard is known for their basic, affordable, no-frills computers. But that doesn't mean they can't keep up with the latest technology. In a press release yesterday, HP said, quote, "We are excited to begin offering that cloud thing that everyone is talking about. We definitely have the cloud on our computers, and it is better than anyone else's cloud." Earlier today, I sat down with HP spokesman Gary Klinman, who said the company couldn't wait to show people, quote, how they do their cloud stuff.
We are absolutely thrilled that now people with computers or phones, both, will now be able to back things up to the cloud. And yes, and that is that's definitely something that people do, and they will be doing it with HP.
HP is making their cloud technology the centerpiece of a major new print and television ad campaign.
HP is the company I've always relied on. So when I decided to get on my computer on the cloud, which is how you do it, naturally HP was the company I chose. HP's cloud is the perfect tool for emails, Facebooks, texting, and CD-ROMs. How does the cloud work? It's so simple and intuitive, I don't need to waste your time explaining it.
Klinman says it isn't surprising they're, quote, up on the cloud, considering they're on the cutting edge of all the latest tech trends. Now, are there any additional features?
Crowdsourcing is something we are having. Crowdsourcing 2.0. We have social sharing. We have 4G, 5G, 6G, really all the Gs. We have app. We have all of it in the computer.
Despite all of their wide array of technology, HP says they're most excited about the cloud. They even let me take a peek at their design laboratory, where HP engineers were trying out some unique development techniques. So, how much capacity will HP's cloud users have access to?
1,000.
We'll be watching to see if HP's cloud push pays off. Make sure to catch the next tech trends when we'll be looking at Body Do, the popular new device that links with your iPhone to post all of your bodily functions right to Facebook.
Okay, so obviously that was not from HP, that was from The Onion. But in all honesty, HP has actually been a pretty good partner with us in determining our hardware configurations. If anybody here from HP, don't be offended. In any case, let me start off by telling you a little bit about Bloomberg as a company. I'll go through this pretty quickly, and then we'll jump into kind of the technical details, because there's lots of them that I could share with you today. And just in terms of logistics, at any point that you have a question, just jump up here and ask it. I don't need to wait to the end to ask questions. If you have one in the middle, by all means, go for it. One thing that I wanted to kind of start off with, which is what Bloomberg does as a company. We offer primarily, our main business is what we call the Bloomberg Professional Service. And we really only service about 300,000 customers, a little over that. And really, we're kind of a big company for just having 300,000 customers, because other than that service, we also have the television station that you've probably seen. We have news radio. There's a wide variety of media in terms of reporting and magazines and things of that nature. There's also other vertical businesses, like a law analytics business, a government analytics business, sports even, for those that are really into sports. The other thing I wanted to kind of give you an idea is the scale of kind of what we deal with on a day-to-day basis. Our messaging platforms, at least for instant messaging, does about 22 million instant messages a day, which isn't really, maybe that crazy compared to some others. about 215 million actual email style messages that are sent back and forth across our infrastructure. A lot of other details there. We collect feeds from maybe about 350 different exchanges, which is really more than anybody else in the world, and about 7,500 other feeds that we get, which actually amounts to about 45 billion ticks a day in terms of events that we ingest, we process, and then we distribute to a wide variety of our customers that are interested in it, which is quite a huge scale, actually, if you think about what you actually need to do it. And just to give you an idea for the timeline, because Bloomberg's actually been around for a very long time. Before really the first web server was written, we had 10,000 terminals installed on people's desks around the financial world. And that actually has led to some very interesting legacy issues, by the way. But on top of that, this is kind of a timeline to just give you a feel for sort of how things were developing in the web world and how things were happening at Bloomberg. So by the time we got to about the 100,000th terminal installed, that's when kind of Google.com was on the map. And then by the time we were about 200,000, you had Facebook. And then today you have about 300,000 terminals installed, and our R&D total was up to about 4,500 people that are actually developing code and writing software for our platforms. And originally, Bloomberg was actually a hardware company because back in the 80s or in 81 when we started, there wasn't a lot of PCs that you could actually put on people's desks. So we actually designed hardware terminals that we put on people's desks. And of course now today that's actually a software-based solution, so it's just an application that runs on your desktop. But we actually still make hardware. In fact, we're actually doing some pretty interesting stuff in the hardware space. We're actually designing trusted computing platforms that are built into our keyboards and into our multi-factor authentication devices that we actually engineer and build in-house. So we actually do a lot of kind of crazy things in the security space that a lot of people might not know about. But that's as much as I'll go into in terms of the history of Bloomberg itself. Let's get to what I'm here to talk about, which is actually the private cloud stack that we've designed. So to start off, what we call this project is BCPC, which is, I've been told by numerous people, is an absolutely terrible acronym for it because it's hard to say. But it stands for Bloomberg Clustered Private Clouds. And the reason that we were designing it is really because using a public cloud infrastructure like Amazon or Rackspace and things like that simply don't work for the kind of infrastructure that we have. We have locality to various exchanges. That's very important for latency of data that we're actually delivering to our customers. Public clouds don't really help you do that very well. It's at least not a great fit at face value. In addition to that, there's also sensitivity of data. When a customer of ours is actually giving us their full portfolios of what kinds of securities they're managing and so forth, we really don't want to be sending that out to a public cloud infrastructure and have that data live somewhere that's outside of our set of controls. Beyond that, we also wanted to make sure when we were designing our cloud infrastructure that we had kind of pure horizontal scaling so that we didn't have a minimal footprint that was large. Because actually we run one of the largest private networks in the world. We have 20,000 router endpoints, 33,000 leased lines that actually compose our private network. And across those, you can imagine that there's lots and lots of points of presence that we have throughout the world. We have about 200 different POPs in different countries throughout the world. And the idea of having programmatically definable infrastructure in those locations is actually a lot more appealing than even having it in our main data centers. Because those are the places that it takes a really long time to get somebody out there if you need to actually replace a box, replace a drive, add some more capacity, and so forth. So having programmatically definable capacity at 200 different small switch closets throughout the world saves us a lot of headache when it comes to having to make fixes, deploy new technologies, et cetera. So the way we've designed these is so that you can build a cloud that's thousands of machines that are actually just all kind of aggregate capacity, or you could build one that's as small as 3 machines. You could really build one as small as 1, but then you really don't have any fault tolerance. In addition to that, one of the things that we were looking at when defining this infrastructure is that, as you can imagine, given the history of where Bloomberg kind of started, we have a lot of big iron systems. That's the core of a lot of our infrastructure. And in those big iron systems, each of your computers is kind of a precious snowflake, right? You give it a name, you give it care and feeding from time to time, you give it patches, you make sure that it's doing healthy and that it's actually happy. In this kind of model, that's not exactly what we're going for. We don't really care about the individual computers. If one of them dies, it dies. We'll have a guy with a shopping cart full of drives come by once a week and replace all the dead ones. No need to give each one a name, et cetera. They're just capacity, and we use them as such. And the idea is that if an individual server fails, we don't really care because we recover our nines in terms of availability on the service layer that sits above it. So there's actually an orchestration service that I'll talk a little bit more about in a second that sits on top of all of these things, and we'll actually see, oh wait, we just lost some capacity over there, spin up some new ones over here where things are still healthy. On top of that, we actually wanted to make sure that our clusters were as standalone as possible so that they didn't have external dependencies that could cause upstream things to make a failure in one of our clusters. Some examples of that are things like DNS, things like having localized authentication resources, having localized access control definitions and resources. So we'll talk about more of that in a second as well. The additional thing is that we've learned from kind of watching a lot of public cloud providers as well as other private cloud installations is to try to avoid anything that would be a single point of failure or anything that would give us, the opportunity for cascading failures. So we try to be pretty diligent about that in our design. As I mentioned before, we actually open sourced all of our chef recipes that are used to stand these kinds of clouds up, and there's the URL at the bottom of the screen there. I'll flash it up here a couple more times, and it'll be on my final slide as well. But going into it, I just kind of wanted to real quickly go through sort of the benefits in terms of infrastructure design when it comes to, kind of our BCPC architecture versus traditional infrastructure. And I'll cover that in kind of two ways. First, from a developer productivity standpoint, then from a production efficiency standpoint. So first, when it comes to developer productivity, the big thing that we were looking to make sure that we could get out of this infrastructure was the ability to give people enough resources so that they could innovate on their own. So if somebody wanted to spin up a couple of servers to try some crazy new thing out, they could go ahead and do so. We could give each developer, here's your bundle of capacity. You can have this many cores, this many gigs of RAM, this many gigs of hard drive space, and they could just go and play with it. They have their own sandbox environment so that they can actually work on things of their own, and that's been tremendously beneficial. In traditional infrastructure, of course, that's a lot harder to do. You have shared systems that a lot of people are working on and so forth, and it's not as easy to not bump into each other. Additionally, from a testing standpoint with traditional infrastructure, you really have to have kind of parallel environments if you want to have a full testing environment, if you want to have a UAT environment, if you want to have an alpha environment, a beta environment. These all require more and more gear in order to stand these things up. With our cloud environments, we basically just stand them up for as long as we need them. So if you want to run testing for a particular module that you have, at the flick of a script, you stand up a whole environment, you do whatever testing you need to do. When you're done, you tear it down, the capacity goes back into the overall. And then in terms of deployment, with traditional infrastructure as well, there's lots of ways that you can actually kind of automate deployment, but the key here is that, with traditional infrastructure, there's a lot of manual configuration that happens. There's a lot of that knowledge that's kind of embedded in the state of your infrastructure that's never captured anywhere else. What we're doing with our cloud environments is basically if you don't have this checked in somewhere into a repository, it doesn't exist. All the machines are configured by automation. There's no way to actually embed any kind of knowledge about how the environment should work in the server configuration itself, because you go and you make a change, it'll get blown away the next time we actually go and refresh that infrastructure. So everything really exists in a code repo where it doesn't exist at all. In terms of production efficiency, and I'll walk through this scaling factor in a little bit more detail in a second, but the general idea is that when you have traditional infrastructure, you really have to plan for how much scale you're going to need if things are to fail. So especially in the kind of work that we do, if you look at sort of the markets overall, people would say that on average the trading volume's down and things of that nature, and it is. But the peaks are actually an order of magnitude higher than they ever were with the advent of algorithmic trading and things of that nature. So if you can't actually handle capacity to the peak, you're failing, right? And so in terms of traditional infrastructure, if we wanted to actually make sure that we could handle those capacity peaks, we have to basically have a lot of infrastructure that sits idle all the time. Of course, with elastic infrastructure, you don't have that issue, right? You just grab more capacity if you need it, as long as you have on the aggregate enough capacity for the overall running of your data center. In terms of developer insight, it's also very tough because when you have traditional infrastructure, you normally have kind of system administrators that run the boxes. You have the developers that write the code. You have some sort of QA process where they QA it, and then there's like a handoff to a deployment team that deploys it, and maybe there's a separate team that's responsible for your application's operational state. That actually makes it very difficult when there's a bug to actually track back to the developer so that they can actually see what's going on, because at some point, a developer is going to say, hey, I need to actually hop on to this production system as root, and then everybody freaks out, right? Because no, you can't give a developer production access as root for security reasons. So in general, we don't really have that issue in this elastic environment. If something goes wrong in production, we just give the developer access as root. They go, they figure out what the bug was, they check it into a code repo, we blow away that instance of the VM, and we start up a new one, or rather, reverse order. We start up a new one and then blow away the one that they had. And then lastly, for security, and I'll elaborate more on this as we go on here, but with traditional infrastructure, you have all the standard traditional infrastructure issues. You have to do machine hardening, you have to do best practices at the OS level, et cetera, et cetera. When it comes to BCPC, you can actually do a lot more things in an automated fashion. You could actually do a lot more things in a way that, that really just gives you a lot of security benefits in terms of declaratively specifying access that you need and so forth. And I'll get more into that in a second. But what I wanted to do next is actually talk through a little bit of the actual technical stack that we use. This may be a little bit hard to see, but I can kind of talk through it verbally. Really, when we were designing our infrastructure, we wanted to kind of focus on using best-of-breed open source tools for each layer in the stack. And so what that started with was basically a bunch of bare metal hosts that were effectively the same. And they don't have to be the same. They were just any host we could find that had that basically were machines that we ended up getting from HP. On top of that, we needed to have a layer that would actually do persistence. And for that, we ended up using the Ceph file system. I don't know if any of you are familiar with that, but it's actually supported by a commercial entity named Inktank. And the Ceph file system is effectively a distributed file system, and I have another slide that talks a little bit more about how that works. But it effectively gives you a reliable distributed object store, and then on top of that, you can build a lot more primitives. So you can actually build block devices on top of that object store, and a number of other interfaces that actually make it pretty good. In terms of reliability and in terms of scalability, it's very scale out in nature. So once we had that persistence layer set up, we were basically using OpenStack as our kind of our programmatically defined infrastructure, but OpenStack itself has a couple of requirements. Namely, it needs a messaging bus, and it needs an actual database to keep state in. So for the database layer, we are using a MySQL. But the problem ultimately with MySQL is that you install it on one node, and if that node goes down, your database is gone, right? And so we ended up using the Galera plugin for MySQL, which is actually a distribution from Percona that gives you actually the ability to keep a multi-master setup of MySQL servers that are all in sync. And if one of them goes down, the rest of the cluster heals from it. It's partition tolerant, so it actually understands if it loses more than half of its capacity that it's not to be active anymore, so it doesn't have data corruption in those particular situations. It actually works pretty well. For the messaging bus layer, we're using RabbitMQ, and we're using RabbitMQ in a clustered fashion. So that RabbitMQ will actually, again, it will automatically replicate to other nodes that are in that cluster and basically make sure that messages are not lost and that they're delivered reliably to the endpoints. And then the OpenStack software itself has a number of different parts, which I won't get into exactly the details of what's actually in the OpenStack components themselves. But the general idea behind it is that each one is effectively a shared nothing design. So it will basically use the RabbitMQ to do messaging back and forth between components, and it'll use the MySQL to actually keep persistent state if it needs to. And so as long as the MySQL layer and the RabbitMQ layer stay up, basically OpenStack is effectively happy. And the way that we kind of do things on top of that, so basically once you have OpenStack installed and configured and all that good stuff, which is no easy feat, by the way. We struggled a lot with this because, how shall I put this? The OpenStack technology is moving rapidly, and it's not quite mature, like so to speak. They've done a lot to actually stabilize it, but I can tell you we've actually submitted a huge number of bugs to get fixed that are pretty pedestrian bugs that you kind of wonder how the heck did it ever work to begin with. But we've managed to get it working, and it's actually gotten, at least in the last 2 releases, into a pretty good state in terms of overall functionality. But then the couple of layers that we've put on top of that, which we're actually in the process of POCing a few different ones, and I think we've actually kind of moving in the direction of building our own, which I might be here a year from now, or maybe at another conference a year from now talking about how we're going to open source that. But it's the orchestration layer that goes on top, because once you have OpenStack installed, really all you have is a bunch of APIs for programmatically making infrastructure, right? You can make a server, you can make a hard drive, you can make a network. That's great, but you haven't actually achieved anything in terms of automating your overall services, right? If an individual service goes down, it's still, rather an individual server goes down, and it's hosting a service that you want, that service disappears. Unless you have an orchestration layer that sits on top and actually looks at all of that and says, hey, that machine just went down, it was holding my foo service and my bar service and 2 instances of each, I need to actually replace that capacity somewhere else in my farm. And then re-add those into a load balancer that's programmatically defined. Unless you have that layer, you really haven't achieved the amount of fault tolerance that you're really sort of looking for. So that's an important piece of the pie. And I think I mentioned this before, but yeah, the ability to actually have clusters that can be made small as well as large, right? So we want to be able to actually send a minimal of 3 servers out to a data center in the middle of nowhere, or out to a switch closet in the middle of nowhere, stand up the exact same stack that we have in our own data centers, and be able to use it in the exact same way. So one of the pieces that I mentioned before was like the Ceph file system itself, and it's based on a concept called RADOS, which is underneath the hood, and it stands for, if I get this right, Reliable Autonomous Distributed Object Store. And basically what it is it's a set of services that actually monitor the overall state of your cluster, and then it actually has these, another part of Ceph is called an OSD, which actually sits on top of a disk and deposits objects onto that disk. And it knows when a disk goes away. There's a heartbeat protocol that it uses between them. It actually runs a Paxos in order to get cluster agreement. And between those 2 factors, if a machine actually dies or if a drive dies, it will actually know that that data is gone missing, and it will re-replicate it somewhere else. The way this works is not through any sort of erasure encoding or anything else. It's straight copies and replicas of objects. And typically, we run our Ceph object stores with a replica count of 3. So for every object that you write into the object store, 2 more are written to other places in the infrastructure, and then your call is returned to say that that object was written successfully. One of the big advantages of Ceph, and then one of the reasons we chose it, is actually it can be aware of your physical failure domains, which is important. You can actually make it aware of what rows machines live in, what racks they live in, and so you can write a replication policy for it that says, okay, I want for every object that I'm storing into this object store, a separate copy kept in a different row and a separate copy kept in a different rack. And so that way it can actually make sure that you have physical fault tolerance in case, I don't know, a pipe bursts in your data center and takes out a row of machines. In addition to that, I'm not going to get too much into sort of the physical topology that we have, but we use 10 gig networking lines for this, and we kind of keep a dedicated 10 gig link for this, because effectively when you're using a distributed file store, you're translating all file I/O into network I/O. And so you need to kind of make sure that you have enough bandwidth for that. And so we end up doing that with a 10 gig link dedicated just for Ceph traffic. In addition to that, the way that all of these kind of clustered systems work is that they need to have a majority plus, or I'm sorry, a 50% plus 1 in order to actually stay up. And so that's kind of the typical way that this works. So that way, as long as there's a partition, if you have an odd number of, say, monitors, you would have 5 total, let's say. If it gets split 3 and 2, the 3 side stays up, the 2 side goes down. A couple of scenarios that I just kind of wanted to walk through that I think probably a lot of these are fairly obvious, but one of the things that we can do with kind of, and so this diagram has on the right-hand side, it has basically what we have in traditional infrastructure when you're deploying on, on the left-hand side rather, we have what you have in the BCPC environment where it's actually being programmatically defined, and then on the right-hand side, we have what is basically traditional infrastructure when you have VMs or individual machines that are running multiple services. So when you're doing something like A/B testing, the idea is that normally you would have, say with this News 1.0 service, we have 50% of our capacity that's being split between these 2 individual services. And if we have to actually do an upgrade to a 1.1 version of that service, in traditional infrastructure, it's very difficult to manage where you have different versions. So typically you would go through an upgrade, you would do a rolling upgrade of your entire farm. So you would actually have to shift off and kill the 1.0 service and then stand up the 1.1 service and then redistribute load. And since you don't want to have unbalanced versions because you don't really have a lot of fine-grained control over how much traffic is being routed to each of these instances, you would then go ahead and do the upgrade on the second one, and then you would have the News 1.1 service that was deployed. In programmatically defined infrastructure, especially if you can do it all through scripting, you can actually deploy a copy of the 1.1 service in a new VM that runs happily alongside the rest of the services that are running the old version, and then you can actually tune and dump maybe 1 or 2% of your production traffic to that new instance to see how it performs, and you can watch it more closely. And then if it actually behaves well, you can then deploy more of them, or you can do a rolling upgrade of the rest. The next scenario that I wanted to talk about, and I kind of talked a little bit about this before, is scaling. So in traditional infrastructure, if we wanted to actually, if we had a situation where we were running really hot, there's really no way to dynamically add more capacity to that until we deploy a new machine, which could take days or even weeks. And once that new machine is deployed, then great, we have more capacity for it. So usually what the implications of that are is that you have to have that capacity pre-deployed. You have to make sure that you have a lot of machines that are sitting there, maybe largely idle, just in case those peaks come along for that particular service. Likewise, when you have the opposite scenario, when things are running cold, you have a lot of machines that are sitting there just sitting idle, not the most efficient setup. Again, with programmatically defined infrastructure, when things are running hot, you can have a service that automatically, again, our orchestration layer, which sees that a particular service is actually running at a threshold. And we use a rising metric and a falling metric for this. And so when a rising metric gets hit to say, you have 80% load for longer than 5 minutes, then it will notice that and say, okay, we need to deploy another one, and so another one will be deployed within usually seconds. And likewise, when things are actually running low, we have a falling metric that says, okay, if you're at 20% load for 15 minutes, then go ahead and reap one. And so then we can go back and kill one and reclaim that capacity in the situation where things are not running hot. And then one of the interesting side effects from this in terms of security is that in traditional infrastructure, you usually have a set number of machines, and you don't have one machine doing one thing. You have heterogeneous software that's actually deployed on all of these things. In our virtual machine capacity, or in our virtual infrastructure rather, we actually try to keep it so that one machine does one thing, or one VM does one thing. And so let's say we had a vulnerability in this News 1.1 service that we rolled out. The implications in terms of the impact of a security vulnerability on your infrastructure is dramatically different. So if somebody were to actually figure out how to exploit this vulnerability that we rolled out in the News 1.1 service, overall, the little yellow stars here kind of show you what all gets compromised in those scenarios, right? A number of different services would be compromised in terms of traditional infrastructure because anything running alongside them on the same machine would generally be in the same domain for that attacker to actually compromise. Whereas in a virtual machine infrastructure, usually you compromise that one VM, you're basically sort of stuck to that one VM. Let me talk a little bit about some of the terminology that we use in terms of the deployments themselves. So I was mentioning before that we kind of have this pure horizontal scale-out model, and really what that means is that we deploy all of our nodes as what we call BCPC work nodes. And those BCPC work nodes are kind of what run the traditional OpenStack infrastructure. They all run Ceph. Basically, they offer up all of their local disks to the overall shared file system, which then gets partitioned and used. And then on top of that, we basically pick randomly from each rack and make one of those boxes what we call a head node. And a head node is basically responsible for doing high availability services, which I'll talk a little bit more about in a second as to how we go about doing that. But traditionally, that's sort of the terminology that we use for it. And the interesting part about it is that you can actually stand up one of these clusters on a laptop. This little MacBook Air that I have sitting in front of me is where a huge amount of the development for this actually got done. You can actually stand it up, you can make VMs, and you can do some VMs inside of VMs depending on your level of inception tolerance. The last thing I'll do here before I talk about sort of the other implications of the infrastructure or just kind of list out some of the open source projects that we use to make all this stuff go. A lot of these are used in kind of conjunction with each other, and I'll talk a little bit more about that in a second. Any questions so far? Good? All right. So let me talk a little bit about how we did high availability and how we tried to avoid blowing our legs off with a lot of this stuff. So the way that we design the infrastructure is that all critical services are always accessed through a virtual IP. And so this is the hypervisors trying to access other services that the hypervisors need. So the OpenStack components, when they need to talk to a database, they're not aware of where the database happens to be running. They always talk to a virtual IP. That virtual IP can get passed between any one of the hypervisors based on, we use the VRRP protocol for actually doing it. And then there's a few other health checks that go along with it. And the idea behind how we do it is that we actually just run an HA proxy on all of our nodes. And that HA proxy is actually, we enable non-local binds for IPs. We bind all the HA proxy listening addresses to the VIP, except only one of them actually has the VIP at the time. So that's the only one that'll actually give out ARP responses for it. And so that'll be the only HA proxy that's actually active. And then each of the configs for the HA proxy happen to proxy to all of the real IPs that are on all the servers. So it's kind of like a traditional sort of architecture you might imagine with HA proxies where you have load balancers on top and then you have a bunch of real servers, except we just kind of squished it and made the load balancers everywhere and then just used a VIP to determine who was going to actually be in the hot seat, if that makes sense. And then for all of the other services that we have, all right? For all of the other services that we have in our stack that actually support a high availability mode built in, we go ahead and use that. And so for Ceph itself, it actually has that HA mode built in, so you actually run a number of monitors. So the Ceph process itself has this thing called a Ceph monitor, and we run that on all of our head nodes. And so that way we have partition tolerance from those. In addition to that, we run our MySQL with the Galera plugin in an HA mode that basically gives us multi-master ability. So you can write to any one of those head nodes and it works. So that way, and everybody that's a client accesses the database the same way through the virtual IP that comes in, gets load balanced across to the HA proxies that sit below it. RabbitMQ, again, we run in a clustered mode, and that basically does kind of the same thing, where it will automatically replicate the messages that are passed in case a node goes down and ensure that they get delivered appropriately to one of the endpoints as appropriate for the AMQP protocol. We also run a directory server that's in a multi-mastered mode, so an LDAP server that sits across all of these nodes and actually gives you the ability to have localized authentication. This is another big part. So if we have, again, a cluster that's sitting in a remote data center somewhere that we can't often get to, if that link gets cut off and it can't talk to our main data center, if it relies on all of its authentication services coming back to some sort of mothership, then the game is over, right? We can no longer use that cluster. So we keep it all embedded, and we actually replicate things and replicate state to each of those LDAP servers or in each of those clusters to make sure that we have that state replicated everywhere so that it can't fall down because of that reason. For anything else that's kind of a database back application, because we have already kind of taken into account the high availability for the MySQL layer, anything that's DB backed can just piggyback on top of that. So we use Power DNS to actually do localized DNS for all of the machines and all of the VMs that get launched in that cluster. We also use Zabbix to do monitoring for health checking and all that kind of stuff for the machines in that cluster and for the VMs and the services that are running there. And then for anything else that was built with kind of a shared nothing design pattern in place, which is namely the OpenStack components in this infrastructure, we basically just run them everywhere. Because you can really, if they're not actually processing a message, they sit there idle and they really just take up a very small memory footprint. And since these are hypervisors, they have kind of tons of memory anyway. Doesn't really hurt much. And then in case of failures, there's always going to be generally one available. In addition to that, we needed to design a few other layers that were embedded into each of these clusters in order to actually make them operationally sound. So that we could actually operate them in a way that a very small group could operate a huge number of these machines or a huge number of these clusters. And so the first is basically doing full automation for bare metal deployment. And so effectively with the recipes that we have open sourced, you can stand up what we call a bootstrap node, which will basically serve as the imaging device for the rest of the machines in your cluster. So if you get a bunch of machines in a rack and you have them all powered and they're brand new, shiny, boxes, you can deploy one that's a bootstrap node. You can pixie boot the rest of them. They'll automatically get imaged. And then a chef recipes will run against all of them and automatically stand up your cluster for you. There's a few steps that you have to do manually in between there. But for the most part, those steps, those manual pieces are just to kind of give you a chance to pause and make sure everything is going the way that you expected it to. But effectively, you can stand up one of these clusters in a matter of a few minutes. In addition to that, we did centralize the kind of directory and name services. I talked a little bit about this before, but the general idea is that if everything has to go remote for DNS, if everything has to go remote for authentication and for access control decisions, then you have external dependencies that are always not going to be there depending on what kind of failure scenarios you're trying to account for. So those are all built in locally into the cluster through Power DNS, MySQL, and 389 directory server. In addition to that, in order to actually manage one of these clusters successfully, you have to have a pretty good way of actually accessing your logs and looking at them. So what we kind of put together was a little tiny utility that's called Beaver that we use to kind of ship logs. And Beaver actually just sits there, looks at your log files, tails them effectively, and then ships them all via 0MQ to what does it ship it to? Logstash, that's what it is, sorry. So it's all shipping them to Logstash that sits on top of our VIP. So Logstash is basically a highly available service that we run in a number of places. Logstash itself doesn't actually talk to each other. They basically can just have a number of them running standalone. So all of the individual servers are just shipping their logs to the VIP. The VIP is then taking them, parsing them, doing the appropriate indexing for them, and then shipping them into Elasticsearch. Well, actually, I guess Elasticsearch is doing the indexing for them. And once they're in Elasticsearch, we have a web front end called Kibana that sits on top of it and allows you to actually go through and look at your logs graphically, get a bunch of nice charts out of it and all kinds of stuff. And so for that, you can actually go through an individual cluster, just hit a particular, particular subdomain off of the VIP, and then you basically can parse all the logs for the entire cluster and see what's going on with the state of it. We also needed kind of detailed telemetry data and stats from each of these clusters that we had deployed. Without that, it was very hard to understand because overall, I mean, there's a lot of pieces of software here, and we use a lot of automation to manage that complexity, but sometimes you still have to sort of get under the hood and see exactly what's going on in terms of I/O, in terms of what's happening with your network interfaces and so forth. And so for that, we actually get a lot of that detailed telemetry data using Graphite. And so we use a small utility from Brightcove that's called Diamond, which basically sits on top of a lot of the metrics that are being kicked out by each host, by each hypervisor, and then it ships them up into Carbon. Carbon sits on top of our VIP, and then it actually relays all that information out to the rest of the hypervisors, so it stores the telemetry data in a highly available fashion as well across our cluster. So again, individual hosts or individual racks of machines going down is not going to actually lose you access to that telemetry data of what happened. And then there's a web interface called Graphite Web that sits on top of it that allows you to do all kinds of slicing and dicing of really, really detailed system metrics of what's going on. And then on the last thing that we have is basically something that would at least tell us when something really bad is happening. And so we use Zabbix for that, for actually doing the health monitoring and alerting. And Zabbix basically, there's an agent that runs on all the hypervisor nodes, and then again, same old pattern that I've mentioned before. We have the Zabbix server, which sits on top of the VIP. There's a number of them that are running. They all kind of keep their back end in MySQL, which is running highly available as well. And so everybody shipping data up can basically get to the Zabbix server. The Zabbix server itself has a bunch of thresholds set in it that will actually tell us if processes die in certain places. It'll tell us if machines are unreachable and so forth. So those are really all the layers that kind of have to do with high availability and kind of cobbling together all these pieces of software into a way that actually makes them kind of a useful cloud. And this took us a while to get working right. I mean, there's a lot of these open source pieces of software. There's millions of people that write blog posts about little bits of it, but getting them all to work together was quite a bit of a challenge in terms of actually getting the overall value from each of these layers. So I've talked a lot about sort of what the stack is and how it works, because I think it was a little bit, I wanted to explain it a little bit, but now I want to shift directions and talk about what I'm really here to talk about, which is what does this mean for security? I've talked a lot about, kind of the technology stack itself and what it does and what it is, but in terms of security, the main thing that is kind of a paradigm shift in the way we thought about infrastructure is that when we're actually building out virtualized infrastructure, we're effectively building ourselves a control plane for servers. Right? Which is not something that you typically have in other places, right? When you talk about network designs, a lot of times every modern infrastructure that I've ever seen has an out-of-band network. They have a control network that they use to actually program their routers, to program your switches and so forth. And then you have your data lines where you actually carry the packets and so forth that are part of the, the running of your infrastructure itself. When it comes to servers and infrastructure itself, there was no such equivalent, but really what we've managed to build here in terms of just kind of shifting your thinking is the hypervisor layer is effectively a control plane for actually peeking in on your servers. So we've managed to do a couple of very interesting things when it comes to security and integrity checking with that paradigm in mind. In addition to that, there's also this notion of compartmentalization, right? In the way that OpenStack works, or at least the way that we've configured our OpenStack installation, because there's a number of ways to do it, each of the tenancies that we deploy on top of OpenStack runs on a completely separated VLAN. And so every VM that's launched in each tenant is basically separate. And we use the notion of tenant, because we're not reselling this, obviously, we're just using it internally. We use the notion of tenant as a project. So for every project, for each service that we want to deploy, we deploy them in a separate tenancy. And that way, there is no logical way or no way for those packets to go between those machines, because it's actually configured on VLANs and the switches themselves, which is pretty big. On top of that, you also have sort of the, for those familiar with EC2, you have the concept of security groups that you can use. And security groups are actually a pretty powerful construct when you start getting more granular about your access control, because a security group is basically a firewall policy inbound for a VM that's enforced by the hypervisor itself. So there's nothing that you can do if you pop a machine and you actually start listening on a whole bunch of ports, no packets are coming in. They will not get to you because the actual firewall policy from the security group is enforced by the hypervisor itself, which is a pretty big change up. In addition to that, A big concept that we use a lot when it comes to our corporate environment is this notion of machine impermanence, which is, somebody does something bad, gets installed, or gets some malware installed because they clicked on some dancing bear's email. We blow away their machine and we reset them back to a known secure state. The same kind of concept exists in our actual data center production infrastructure now, because we have this notion of what was the gold image that a particular service was launched from. And we can then, if something goes wrong, blow it away and just start a new one. And we know that that one's going to be, at least going to start out being safe. Of course, we still need to do some work on figuring out how the first one got popped, of course. But yeah, there's actually that very quick notion of returning it to service. In traditional infrastructure, of course, that's much harder, right? You have to actually do forensics on the box. You have to figure out what else was compromised. Did they actually bounce anywhere else, et cetera? But between compartmentalization and the ability to reset something back to a known secure state, we can eliminate a lot of that risk very quickly without having to spend a lot of time making a lot of hard decisions about what risks we think are possible. So now let me talk a little bit about some of the security layers that we're in the process of building right now. Not all of these are completely done and deployed to production yet, but these are all kind of in the works. Some are a little further than others. The first is automated security patching. Security patching, it's been a best practice in the security space for how many years? Like since security was even a thing it's ridiculous because it's a painful problem that almost every company struggles with, which is how do you actually keep machines up to date, how do you patch them, and so forth. So with this kind of infrastructure, one of the first things we designed was a method of actually doing automated patching so nobody actually has to pay attention to it. And the idea is that in order to actually do automated deployment of your software to a VM so that it's automated from the moment you check some code into Git, it goes through a Jenkins server, it gets automatically built, it then gets deployed onto a VM, and then we run some health checks against it. The idea is that when you have a new patch version that you want to do, you actually would bring up a machine, you would patch it, and you would rerun the set of health checks. And then you maybe do that to one machine on day one. And then you report it to the NOC. And if the NOC says nothing, if they don't notice any red lights blinking because we patched one machine and that machine seems to be healthy and it's running the service well, well, then the next day or the next week, depending on how fast or how aggressively you want to roll out your patch, you could then do, say, 20% of the machines. And then you alert the NOC, and you alert the dev team that's responsible for that piece of software. And if no red lights blink and everything is happy and the health checks are passing and nobody says anything, then in the next week after that, you do 50% of the machines, and you alert the NOC, you alert the dev team, and you alert the business group responsible for that service. And then again, same process. Nobody says anything, all the lights are happy, the health checks are passing, great, we do the rest of them and nobody has to care. So the process just occurs in the background without anybody having to really pay attention to it unless something goes wrong. And there's two possible things that could go wrong. One is that the patch actually breaks your piece of software, in which case somebody ought to know at the first stage, or at least by the time you get to 20% and your developers got notified, because they'll say, hey, this is actually causing our application to screw up. We need to go back and look at what this patch actually did. The second scenario is that the patch screws something up, but the health checks still come back green. And the good part about that is that the impetus is in the right place, right? Because you have your developers that are actually writing your health checks, and if they write a health check that's still green, even though the software wasn't working right, it's their fault. They can go fix it. They can write a better health check to go do it. So it actually kind of puts the impetus in the right place to make the improvements that you need in order to do this automatically. Okay, so that's patching. The next piece to talk about, which I thought is kind of an interesting one, is actually doing automated runtime integrity checking of running VMs. The idea here, the basic concept, is that when you're launching a VM, you're launching it from some image that you have, which is either an image that you've baked an application into, or it's an image where you've launched it from some generic image, and then you've installed an application on top of it, depending on how you run your clouds. The idea is that we've built a kind of a system that does automatic integrity checking against it, because you can build a rule set for each of these, and what will happen is effectively in the background cycles of a hypervisor, it will mount read-only your file system of your VM at the hypervisor, and then it'll actually run effectively a tripwire-like check where it'll actually hash the file system for each file that's on it, and each of your rule sets will tell you what's allowed to change in each one. So for an individual image, like an Ubuntu image or something like that, you'll know that Etsy hostname is going to change on every boot, et cetera. There's going to be a small set of files like log files, et cetera, that you're going to want to exclude. But you're going to know those a priori, so you can actually catalog those in kind of a rule set that says these are the files that are allowed to change as the machine is running. But at the moment that something changes that you're not expecting to change, then you can actually automatically respond to that, right? So if somebody actually breaks into a machine and ends up dropping a core file somewhere, that machine can automatically be frozen in time and just set aside for somebody to go look at, right? Or as soon as the integrity check runs. Again, it depends on how aggressively you actually want to run these integrity checkers in the background. But effectively, it basically gives us kind of a non-bypassable tripwire. Because one of the first things that you do when you actually are breaking into a machine that's running tripwire is you look for it and you try to disable it, or you try to actually just pass it back a different data set. In this particular case, it's non-bypassable because it's happening at that control plane, at the hypervisor layer. There's no way to actually do that per se, and that's, I'll put a little asterisk by that. But yeah, so that in general is the idea. The last thing that we're working on right now that's going to be a pretty big one by the time we get it done in terms of efficiency as well as security is automated provisioning of our network ACLs. For most organizations, especially one as big as ours, that we run such huge networks that have kind of a lot of different purposes and they're very segmented in nature, managing firewall rules becomes a real big pain because you need to figure out, is this particular access okay for whoever's requesting it? And normally, by the time it gets to like a network group that's supposed to be pushing a firewall rule to a set of firewalls or to a set of ACLs on routers, they're basically looking at like the trees. They're no longer looking at the forest. They see like IP 1.2.3.4 port 400 going to 4.3.2.1 port 7500. Like, what does that mean? They don't know what that traffic is. They don't know what it's supposed to be. And they've sort of lost all the granularity that they would need to make an informed decision about whether or not that's a good idea. So what we're actually moving towards is doing a more declarative style of ACLing based on a service. So when you're building a service, if I'm building the foo service, I could declaratively specify that I need inbound access from the bar service and outbound access to the QUC service. And then when I actually go about deploying these services, I never have to worry about where they're living because the orchestration layer actually knows where it's put each of these things. It actually knows what IPs and what ports they resolve to. And then it can actually say, all right, I'm going to hit the API on this particular firewall and program it to actually allow these particular ports to talk to one another. And then you're done. You don't have to worry about it anymore. You can actually look at it at a level that actually makes sense to you as a security professional, right? You can say, okay, bar is supposed to be able to talk to this, and this is supposed to be able to talk to bar, so we're good. I don't really care where they're deployed as long as it's managed by my orchestration layer. The right things are going to happen. And so that's a pretty big improvement in terms of how we specify networks. So the last kind of set of things I wanted to talk about is some additional security topics just to play around with. I mean, these are just ideas that we've had. We have not gone further down the road with them, but I think they're kind of interesting ideas either for research or for tinkering around with at the very least. And that's actually doing hypervisor level integrity checking of processes that are running in the VM. To either verify them from a signature perspective, to verify them from what's running in terms of their memory footprint, even in terms of like hooking the VM in various ways to determine if those processes are actually following a particularly well understood behavior pattern. After you've run these things for a while, you could do some modeling and some data gathering of what your individual processes inside of VMs are doing, and then you could actually start to abstract that out to say, okay, maybe this is a policy that I want to start enforcing for this particular process, and sort of a learning and then enforcement mode down the road. Another idea that we had is to actually utilize trusted computing devices. So I mentioned before, we build a few different trusted computing devices. And actually using that for enveloping a VM from the hypervisor itself, so that a hypervisor could actually run a VM without actually knowing or being able to see anything about the VM. So it would basically be kind of a blind VM. This is one that's more, you might think that it's more for like a hosting provider, but there's certain situations that we've come across that would be kind of a beneficial technology to have. So we could actually utilize a trusted computing device that we put into a hypervisor such that it would be the only thing that could actually run a particular VM, and the VM itself would be enveloped by a separate trusted computing device that will have been pre-paired with the one that's in the hypervisor itself. Again, this is pretty researchy at this point. We're not too far down the road for it, but I think you can actually use trusted devices to make these kinds of guarantees ultimately. And then the last one that's kind of really an open-ended question, which is further protections against any sort of vulnerabilities or attacks that would allow you to break out of a VM into a hypervisor. All of this stuff that I've been saying about the hypervisor being a control plane is all contingent upon the fact that you don't want there to be any vulnerabilities or any ability to break out of that out of the VM into the hypervisor itself. And so we've done some of the basic things in terms of address like ASLR and DEP and that kind of stuff in terms of preventing execution of data pages, as well as preventing or rather randomizing address-based layout. But I think there's a lot more to be done there in terms of hardening it, and really this is one that's just kind of an open area of research in terms of how do we actually get some more assurance around making sure that that's not possible. So with that, I will open it up for comments, questions, flames.
Felix Lindner, Security Labs. Have you looked at private core for the isolation of virtual machine and hypervisor?
What was it again?
Private core. Private core is a hypervisor that doesn't know shit about what's running in a VM.
I haven't, actually.
Check it out, it's good.
Yeah, it's interesting. Cool.
Hi, Yu Sun from Penn State. So I can say you replicate the database and message queue for high availability. So did you also consider the secrecy and integrity of the database? So if one of these database services gets compromised?
So the database that we actually run at the hypervisor layer is not ever going to be used by any clients. So it's only ever used by the services that are deployed and running on the hypervisors themselves. So we have less of, I guess, kind of risk. We're not trying to run, basically the way we divide the world is anything that's hypervisor scale versus anything that's VM scale. So the database and the message queues and things like that that run on the hypervisors only ever deal with services that are hypervisor scale, meaning the other services that are on the hypervisors. So if a VM wanted a database, we would just deploy a separate database somewhere else, not on the hypervisor itself, but into a virtual machine for that application.
Okay, so that would incur a very large trusted computing base, right? So every replica database would be included in this TCB.
How do you mean, like, I'm not sure I'm following the question.
So the entire infrastructure needs to be trusted, right? The entire infrastructure.
Well, I think our hypervisor layer is considered trusted, and anything that's running on the VM layer is not.
Yeah, okay. Thank you.
Yep.
Hi, Aaron Temin from MITRE. Thank you for coming today. You talked a lot about defenses and not so much about the attacks you were trying to defend against. Is there particular aspects of the threat model or expected attacker that you'd be willing to share with us that wouldn't be considered too proprietary? You're more interested in insider threat or outsider malware, denial of service?
Yeah, well, I think the main ones were insider threat as well as kind of advanced attackers, right? And the main, like denial of service wasn't as big of a concern, although it sort of is benefited by this infrastructure because as long as you have enough capacity, you can actually handle a DOS against a given service a lot better as long as you have an orchestration layer that'll scale up and down. But without getting into too many specifics, I mean, it was really getting people's, like insiders' hands off of machines so that it's all done through automation and it's all auditable in terms of what's going to happen in terms of configuration of a box based on scripts that are checked into a code repo that we can attribute. And then there's also sort of the more advanced attack, which is where the compartmentalization and the impermanence factors kind of come into play, where we wanted to be able to know that we have a very hard limit in terms of a machine gets popped, what can it actually talk to? And then from there, if a machine gets popped, what's our defined timeline to removing malware, even ones that we can't detect?
And maybe I missed it, but did you have something in place that was looking at the possible data exfiltration? It looked like everything was looking at running processes and not at where the data was going.
Yeah, we're not really looking too much at data exfiltration. From a service standpoint, we have various measures in place that actually prevent people from taking data from the hypervisors, because that's sort of where people log into, and that's more of our traditional infrastructure access. When it comes to a given service, those are all sort of deployed through automation, so the code is checked. So if there's a way to kind of exfiltrate it, we will have a record of it somewhere, but we're not actively monitoring for particular kinds of data leaving.
Thank you.
Hi, Stefan Sorio, Microsoft Research. Thank you for your talk. I had two questions. The first one is more of a clarifying question. You talked about trusted computing devices. And can you tell me what you meant by that? Do you mean TPMs or you mean something else?
I mean something else. I mean,
okay, so what do you mean? Yeah.
I mean,
what's a trusted computing device?
So I really mean kind of basically PCIe cards that are HSMs.
Yeah. Okay.
Yeah, and so we do that. We actually have, I don't know how much I can talk about this, but we actually have designed our own HSM that runs as a PCIe card that you would put into an individual chassis, and then that OS would be able to access it and kind of use it like a normal HSM.
Okay. Okay, and my second question is, you talked about, sort of the ability to sort of introspect the running state of a virtual machine, sort of the in-memory state and things like that. And then you talked about ASLR. Can you tell me a little bit sort of what's your, like, how can you do both? How can you actually scale sort of understanding what the state of the machine is when you have address space randomization?
So the ASLR piece we were actually using on the hypervisors themselves as a protection against attacks that would allow you to break out of a VM reliably and to get into a hypervisor.
I see.
And then the VM introspection was more from the hypervisor looking into the VM.
Okay, thank you very much.
Hi, Jeremy Epstein, National Science Foundation. NSA announced the other day that they're getting rid of 90% of their sysadmins to reduce the insider threat, which I find kind of amusing. Do you have so my first question is, do you have a perception of roughly how much you can get rid of by doing some of this automation you're doing? Of course, we don't know how many they started with, so 90% may be a little or a lot, but do you have any perception what you can do? And then my second question is, you're throwing a huge amount of software into your system to help automate it. How much do you perceive that you're increasing the risk, or do you think it's increasing the risk because you have a bigger attack surface potentially with all that additional software?
It's a good question. For the first, in terms of overall reduction, I don't really have a great feel for it yet. I mean, our goal in doing this was not really to reduce the amount of people that it took to run our infrastructure. The main goal was actually to reduce the amount of people that needed to have access to systems on a day-to-day basis in terms of going in and tinkering with things and manually fixing.
I think NSA would like that too.
Yeah, I think that was the main goal, because I think inherently that reduces your insider threat profile, right? If there's less people with less access, sort of the principle of least privilege, right? So, I guess in addition to that, when it comes to staff reduction, that wasn't something we were looking for. Like I fully suspect that all of the folks that we have right now would just be off writing code to do different things, right? Then the second, remind me the second question again?
Are you increasing your threat surface, your attack surface?
So the short answer is, obviously, right? We're installing a lot of pieces of software that we previously weren't running in a lot of places of our infrastructure, and on each of our hypervisors, there's a lot more stuff running on it. But what we've actually done is made it so that all of those systems are actually talking to each other. So really, there's one front door to talk to a cluster, and that's our VIP. So anybody else that's outside of the local network that it's on. So all of these are front-ended by a firewall that only ever lets things into the management interface that's on the virtual IP. And so the virtual IP is what hosts our API services and so forth. And so we can actually watch that fairly easily. So we can actually audit the traffic that's going in there. And most of that is all happening at effectively human scale, right? Because it's people that are actually writing a script that fires up some VMs and does things of that nature. So most of the software isn't exposed anywhere. So it's not like I, from the outside or sitting at my desk at work, can actually talk to, I don't know, let's say the Logstash port or the Elasticsearch port. They're all just talked to by the internal services inside of that cluster, and I can't get to them from the outside. I can only ever kind of talk to the user consumable services like the API endpoints and the web front ends for all of these services from that VIP.
The reason I'm asking is Aaron ran a very interesting workshop a few weeks ago where we talked about does more software mean more complexity? And the obvious answer is yes, but the more you think about it, I'm sorry, the question wasn't does it add more complexity, does more software mean more security risks? And the answer may be yes and maybe no. In your case, arguably more software is leading to less risks, or fewer risks, because you can automate some things and reduce insider threat and so on. So it's not always obvious that more is bad.
Yeah, I would say so. I mean, I think that one of the things that I freely admit to is that this is like our architecture is fairly complex, and it's easy to argue that more complexity would probably lead to a less understanding of what's going on, therefore potentially more security vulnerabilities. But the way we've tried to manage that is by doing it all through automation. We use chef recipes to stand it all up, so the complexity is actually codified in code. I mean, there's applications that do things that are far more complex than standing up this infrastructure that are way less easy to understand than the recipes that we've put together. But we just, typically you don't think about it that way from an infrastructure standpoint. But if you can codify the deployment of your infrastructure as code, then all of a sudden that complexity becomes a lot easier to manage. You manage it through the same way you manage software complexity. which is by factoring things out into good modules, to making sure that you have the right level of granularity on the pieces you're standing up, to making sure you have good compartmentalization and barriers between the layers, like encapsulation of the layers of your infrastructure. And so that's the way we've tried to manage the complexity with it. But it is more complex, you're absolutely right.
Thank you.
So I had one question. Want to first get your opinion about how homogeneous versus how heterogeneous you think the applications are, because I think this has a large impact on how successful you're going to be with some of the techniques you're talking about. So you have all these abstractions floating around, where that abstraction is a group of VMs that the orchestration layer is dealing with, or you have the hypervisor introspecting on an individual VM or VMs. Obviously, we know the semantic gap problem for that introspection, and so there's a lot of work that has to go in about teaching the lower layer about the higher layer that it's introspecting on. I can imagine you having similar sets of problems with the orchestration layer. So you were talking about rolling out new services with patches, or killing a box when it gets owned and return it to a gold state. But there's a lot of things that happen in terms of persistence in those applications that only the application developers are going to know. Do I have to roll back transactions as a point of doing this? What do I roll them back to, for example? So I'm wondering a little bit of how you deal with, so is it just simply the case that you have lots of applications that all run on the same operating system, so the introspection becomes easier? Do all the applications sort of have the same design pattern, so it becomes easy for the orchestration layer to deal with it? Or how do you deal with, at either one of those abstractions, this notion of lots of heterogeneity and trying to do all the special things and deal with that?
It's a really good question. So we absolutely don't have homogeneous applications. We've got stuff that comes in all shapes and sizes, especially in terms of what models they use for persistence. We have all the databases in terms of relational and NoSQLs that you can think of. We have in various parts of our organization. We have a lot of different kinds of app architectures. The one thing that we do have that helps a lot is that we have kind of a very strong SOA infrastructure that is, you can think of it as being very SOAP-like. It's not SOAP. It was kind of built before. That was kind of a standard. But there's XML specs for service endpoints that show you, these are the endpoints that you can call. These are the pass-in parameters, the pass-out parameters, and that kind of thing. So we have a bit of a strong specification that helps us a lot in terms of what the service should be passing in and out. But in terms of recovering persistence layers, what we've tried to do is two things. First, we tried to standardize everybody on some centralized and centrally managed persistence layers. So we have an S3 object store that we use that we routinely snapshot for each individual kind of pool or each bucket, so that we can actually roll them back to kind of a known good state if we can figure out exactly what happened, if our automation catches integrity failures early enough. And then we have kind of a shared key value store that we use that's kind of cross data center, eventually consistent, that kind of thing. And so we've been migrating a lot of apps to that. But we still have plenty of apps that still use a traditional MySQL backend and Redis and Cassandra and all that kind of stuff. And so for those kinds of applications, what we've been doing is kind of migrating them into our cloud environment, but trying to set up recipes for standing those same kinds of tools up so that no group has to kind of figure it out on their own. So once we kind of make a Cassandra recipe that'll set up a multi-endpoint, highly available Cassandra, we just allow everybody to use those same chef recipes for it. So we're standardizing on what I call our utility instances. And those utility instances, we build good parameters around so that we know how kind of the database layer works. If we're going to use, like, say, a persistent volume to actually back it, we will have a schedule set up that will snapshot that persistent volume on a routine basis based on what the app is doing. And so we try to basically just keep enough of a trail behind those persistence layers, so if something does go wrong, then we can actually go back and reset it to a no good state, or at least have a good audit trail of what changed between each stage.
Toan from Carleton University. So you mentioned about the firewall rules. I'm wondering, do you have where you actually enforce these firewalls? Do you have hardware firewalls, or you enforce in the switching route device or in the VM themselves?
Not in the VM, and it's split between hardware firewalls and the actual hypervisors themselves. So when we're talking about like the concept of like security groups and things like that, those are all enforced by the hypervisors, and that's as much as we do with automating IP tables and things like that. And then for the rest, we're talking about basically all of our clusters are front-ended by a Palo Alto firewall, and we use the APIs on that to actually allow services inbound or outbound access from a given tenant or from a project. And so what we'll do is actually have a piece of automation from our orchestration layer that actually will programmatically tell that firewall, hey, add this to this rule group, or add this floating IP to this rule group so that it can have the same policy that was predefined.
Okay. So let's say if you have like internal traffic from VM to VM, so does that traffic go through this hardware firewall, or it doesn't go there?
There's actually a number of different scenarios with that, because if it's inside the same tenant, then those two VMs are on the same VLAN.
Yeah.
So typically they would be able to talk freely unless you've also specified a security group for those. And if you've specified a security group for those, then they wouldn't be able to talk freely between each other. Then normally what you would do, well, the other scenario, so that's within a single tenant, because they're on the same VLAN. If you're on two separate VLANs or two separate tenancies, then you can't talk to one another until you kind of go out of the infrastructure.
Okay.
And typically what that means is that you would actually need to make a publicly addressable IP assigned to each of these VMs, and then they would be able to talk to one another.
Yes.
And then that would actually go up and down through a firewall, so we can enforce policy there.
Okay, so if you, inter-tenant communication will actually go through the, say, external gateway, it will be redirected to the firewall, then go back.
It's a little, there's actually like 3 or 4 more scenarios that are kind of complicated for me to explain verbally, but yes, typically it will either go through the north-south firewall, or it will, in some situations, we will actually allow it to go east-west without actually going north-south if it's something that's allowed. But like if we take 2 tenants, and it's a little complex, but like the idea is that if we might have 2 projects that are very closely associated with each other. Let's say, for example, I have one tenant that I put all my databases into, another tenant I put all my web front ends into. And I want to keep those more closely associated. I don't really want all of that traffic to go north-south for efficiency's sake, so I'll actually associate those a little bit lower in the stack in terms of allowing the hypervisors to talk directly to one another.
Okay, so in this case, the firewall rules will be enforced on the hypervisor, not through the...
Yeah.
Okay, thank you.
Yep.
So if there are no more questions, can we thank the speaker again, please?